In this video, we're going to look at the graphs of the sine and cosine functions. So a common misconception among beginning trig students is that the unit circle is a trigonometric graph. The unit circle is just a tool that's used to represent the values of sine and cosine and then all of the other functions in terms of sine and cosine respectively. So you can think of the unit circle as just a tool that summarizes all the different right triangles you could draw with any angle, all the way from 0 to 360 degrees or 0 to 2 pi, and then of course onward from there depending on how far you continue to rotate. But the unit circle is not actually a graph of a trigonometric function. It's just a graph whose coordinates happen to represent those individual trigonometric values. But if we were to pull the individual coordinate values out from the unit circle, then what we'll find is individual values corresponding to sine and cosine. And then again, of course, we can combine those different values in different ways in order to get the values of the other four trigonometric functions. So individual trigonometric functions have their own individual graphs, and we're going to talk about how you would graph each of those individually. So here we're just going to focus on sine and cosine, and then we'll look at the other four functions a little bit later. So we're going to generate our graphs using the radian measures as our inputs, so the radian measures, and the coordinates as our outputs. All of these that we find from the unit circle. So the radian measures are going to represent our x values, our inputs. Again, think of those as representing the rotation around the unit circle, but also we like radians rather than degrees when we talk about rotation because radians allow us to relate rotation and length. So if we were to think of wrapping a number line around the unit circle, then the radian measure that tells us how far we've rotated around the unit circle can also be used to represent a distance along that number line. So radian measures around the unit circle are going to represent our functional inputs. We plug an angle value into a trigonometric function, and then the coordinates around the unit circle, the x, the y, or some combination thereof, are going to represent our specific outputs, our specific values for our trigonometric functions. So we'll look at those values in a little more detail in just a minute. You will of course want to have a filled-in unit circle available so that you can look at some of the numbers on there to help you graph. Now what's going to be unique about these graphs that we haven't seen with any graphs before is the fact that these functions are periodic. They repeat. So the outputs of the sine and cosine functions repeat over time, over a specific period of time. And we talked a little bit about the periods for those functions before. When we look at the actual graphs of our trigonometric functions, we see the periodicity in the sense that the graphs are going to repeat. So the shape of a graph repeats. The graphs repeat specifically in the shape of a wave. So if you've ever heard the term sine wave or cosine wave, they're referencing these particular graphs, and in saying that the graph is shaped like a wave, we're saying that the outputs for these functions repeat over a specific period of time, and we have a shape that just continues indefinitely either to the right or to the left. So let's talk about the sine function and its graph specifically. So again, we're going to think of our input x as our radian measures, and notice I'm just looking at the radian measures there, those quadrantal angles, specifically going from 0 radians to 2 pi radians. And then the output is going to be the value of the sine function associated with that particular radian measure. So if we're looking at the unit circle, starting at 0 radians, remember on the unit circle we've defined the sine as our y-coordinate. So the x-coordinate at any particular ordered pair on the unit circle corresponds to our cosine, and then the y-coordinate corresponds to our sine. So if we're at 0 radians, our sine value is going to be 0. So for our actual sine function, if we input a radian measure of 0, the value of sine is also going to be 0. Now, as we travel around the unit circle in the positive direction in the first quadrant, starting at 0 radians, we're going from 0 radians to pi over 2 radians. I want you to think about what's happening to the value for sine. So remember, sine represents our y-coordinate. As we travel around the unit circle, going from 0 radians to pi over 2 radians, our y-coordinates are increasing, and they increase until they get to a y value of 1. So once we reach pi over 2, the value of our sine function is going to be 1. Now, once we reach pi over 2, and we continue rotating, notice that now the y values will start to decrease. So they're going to decrease all the way back down. Once we get to pi radians, the y values have decreased to the point of reaching 0 again. And then if we continue to rotate, now we've dropped below the x-axis, which means our y values are now negative. So as we continue to rotate from pi radians to 3 pi over 2 radians, we're decreasing from a value of 0 to a y value of -1. So at 3 pi over 2, our sine value is -1. And then as we come full circle, we continue rotating from 3 pi over 2 all the way back to 2 pi. We get back to a y-coordinate of 0. So we can think of each of these as an ordered pair that exists on the graph of the sine function. So the radian measure is going to be our x value, and then the value of the sine function, its output associated with that radian measure, is going to be our y-coordinate. So let's put these specific ordered pairs on our graph. Now we need to label our x-axis with our radian measures, and then we also need to label our y-axis. Now notice the y values go from 0 to 1 to 0 to -1 to 0. But based on the fact that we're on the unit circle, the highest y value we can reach is going to be 1, and the lowest y value we can reach is going to be -1. Anything beyond that will fall off of the unit circle and doesn't apply. So that means our sine function stays within the y values from +1 and -1. Okay, and then let's label our x-axis with our radian measures. So we have 0 radians. And then once we rotate around the first quadrant, we get to pi over 2 radians. Continue rotating, we get to pi radians. Again, continue rotating, we get to 3 pi over 2 radians. And then we come back full circle once we get to 2 pi. And what I want you to keep in mind is we were rotating, in theory, from 0 to 2 pi, but because the unit circle can continue, we can continue rotating around. All of these values would then repeat because we're looking at the y values on the unit circle. We only have a finite number of y values, or technically we have an infinite number, but those values are going to repeat. So once we go past 2 pi, we're going to end up with repeating y values, or once we go past 0, we're going to also end up with repeating y values. So we're just going to look at this one little snippet here from 0 to 2 pi, since this represents a single rotation around the unit circle. And again, if we continue to rotate, we're just going to see the same behavior. So let's graph the actual ordered pairs we have. So when x is 0, the associated y value is also 0. When x is pi over 2, the associated y value is 1. And notice 0 to pi over 2, that means we're rotating around the first quadrant. And as we go through the first quadrant, the values for our sine increase. So they're going to increase, and we end up with a shape something like that. Now once we reach pi over 2 and continue to rotate, now our y values are decreasing again. As we go from pi over 2 to pi, our y values are decreasing from a maximum of 1 back down to 0. So when x is pi, when we're at pi radians, our sine value is 0. So again, we continue, but now our sine values are decreasing. Now once we get to pi and continue rotating, again we drop below the x-axis, so now our y values are going to be negative, and they minimize down at -1 once we reach 3 pi over 2. So we're decreasing down to -1, and then once we get to 3 pi over 2 and we continue to rotate, we're increasing, but still within the range of negative y values, but we're increasing back to y equals 0. Once we come full circle. So what we have here is what we call one period of the sine function. This is essentially a snapshot of what the entire function is going to look like. If we were to continue rotating either in the negative direction past 0 radians or in the positive direction, past 2 pi radians, what we're going to find is that the graph essentially just repeats in the same way forever and ever and ever. This is the idea of a periodic function. But if we want a sense of what's happening with the periodic function, all of the important values, all of the unique values, all we really need is this one period. So as we graph our functions, typically we're just going to focus on this one particular period from 0 to 2 pi. What happens with our function when we add in different numbers, we'll talk about what that means. But specifically as we graph, we'll typically focus on just one period, starting and going across a whole rotation of the unit circle. Now from this graph we can also start to talk about domain, range, and then symmetry that we see from the sine function. So the domain, remember, that's going to represent our inputs for our function. Well, this graph is going to continue forever and ever and ever, no holes, no breaks, nothing like that. We covered the entire real number line along the x-axis. So our domain is going to be all real numbers. Now our range, that's the y values that we cover, and the range is very much dependent on the behavior we see on the unit circle. We're getting our y values from the sine values that we see on the unit circle. Well, we started at 0, and as we rotated in the positive direction, the highest y value we reached was 1, and as we continued to rotate, the lowest y value we reached was -1. Because we're confined within the unit circle, we can't actually pass a y value of 1 or a y value of -1. So that means our range is just going to be the real numbers from -1 to 1 inclusive. Now the symmetry we see here with the sine function, we can see if we were to continue to graph, our sine function is actually going to have origin symmetry, which means if you were to take one portion of the graph, reflect it vertically, and reflect it horizontally, it's going to coincide and lay on top of itself. This is also very closely related with the idea that the sine is an odd function. Any function that happens to be odd, its graph is going to have origin symmetry. Okay, so now let's talk about the cosine graph. We're going to see a lot of similarities from the cosine graph, and again we're going to get our values based on what we see on the unit circle. So same inputs, we're going to look at the radian measures starting from 0, going all the way to 2 pi, in other words that first full rotation around the unit circle. And now our outputs are going to be the values for cosine. Now cosine is represented by the x-coordinates on our unit circle. So this is kind of misleading. This is typically a little confusing at first. Here this x we're thinking of as our input for the individual cosine function. And the cosine function is going to take angle measures as its input. But when we talk about the actual value for the cosine that we're getting from the unit circle, the value we get from cosine is represented by the x-coordinate on the unit circle. So this x is x with respect to our particular graph, and the x that gives us cosine is the x that we get from the unit circle. So rather than thinking of it specifically as x and y on the unit circle, just which value represents sine, which value represents cosine. In this case, as we look at the coordinates going around the unit circle, the first coordinate is going to represent the value for our cosine. So when we're at 0 radians, the value for our cosine, the first coordinate, has a value of 1. So at 0 radians, our cosine has a value of 1. Now, as we continue to rotate, we're rotating from 0 radians to pi over 2 radians. What's happening to the value of cosine? Well, if cosine represents our first coordinate, the first coordinate is actually decreasing as we rotate around the unit circle. It's decreasing, so as we once we go from 0 to pi over 2, the first coordinate has decreased from 1 to 0. Now, as we continue to rotate, now we've gone past the y-axis, which means that our first coordinate, our x-coordinate, is now going to be negative. So we drop into negative values for our cosine. So we go from 1 to 0, and then once we reach pi radians, we've reached a first coordinate of -1. If we continue rotating around to 3 pi over 2, Our x values are still negative, but now they're increasing again. So we increase from -1 up to 0. And then yet again, as we continue rotating around and we come full circle back to 2 pi radians, we're now into positive x values again, and our x values continue to increase until they reach 1 again. And this is also going to give us those key values. Again, notice that the radian measures are the same, but we have different values for the actual function. They come in a different order if we're looking at cosine. So again, we need to label our x-axis, we need to label our y-axis. Now, just like with the sine function, because the cosine function is defined based on those coordinates on the unit circle, we see a lowest value of -1 and a highest value of +1. Again, because we're confined within the coordinates represented on a circle of radius 1. So that means the highest y value we're going to reach is 1, and the lowest y value we're going to reach is -1. And then again, we're going to put in our radian measures. So as we rotate around the first quadrant, we go from 0 to pi/2. Rotate around the second quadrant, we go from pi/2 to pi. Rotate around the third quadrant, we go to 3 pi/2. And then rotate back to where we started, and we end up at 2 pi. And so now let's plot these ordered pairs. So when we're at 0 radians, the value of our cosine is going to be 1. So whereas sine started at the origin, if we were to look at the sine graph, it starts at 0, 0. The cosine graph is not going to start there. When we're at 0 radians, the cosine function has a value of 1. So it's actually going to start up here. Now as we continue to rotate, again, the cosine value, the first coordinate on the unit circle, is decreasing. So it's going from a maximum of 1, and then once we get to pi/2, it's decreased to a value of 0. So it's decreasing as we travel the first quadrant. Now as we go from pi/2 to pi, again, now we're on the left-hand side of the unit circle, where all of the first coordinates have negative values. So we continue to decrease from a x-coordinate of 0 to an x-coordinate of -1. So our cosine drops down to -1. Once we continue rotating to 3 pi/2, now we're increasing again. So we're still in negative values, but we're increasing again. Our x values are getting bigger again. And once we get to 3 pi/2, we've made it back to 0. And then once we come full circle, go back to 2 pi. Now our first coordinate is positive again, and we increase from 0 to 1. And so that's going to be the graph, single period, of our cosine function. As with the sine function, because these values are representing rotation around the unit circle, we could continue to rotate in the positive direction, or we could rotate in the negative direction, and we're going to see all of the same x and y coordinates, so all of the values for cosine are going to repeat. So we would have the same shaped graph forever and ever, continuing in either direction. If we were to continue graphing, look at different radian values. Now, what can we say about domain, range, and symmetry for our cosine function? Well, again, our graph covers the whole real number line, the whole x-axis, no breaks, no holes, nothing like that. So our domain is going to be all real numbers. And then just as with the sine function, because our cosine is generated from values on the unit circle, the highest value we can reach on the unit circle is 1 in any direction, and the lowest value we can reach is going to be -1. So our range is also going to be -1 to 1 for this function. Now the cosine graph has a different type of symmetry. If we were to continue the graph in either direction, specifically focusing here on what happens around the origin, notice the graph is going to have a mirror image of itself across the y-axis. So we specifically have y-axis symmetry for our cosine function. And that's associated with the fact that cosine is an even function. So it's going to have y-axis symmetry. So these are going to be our basic graphs, the basic graph of sine, the basic graph of cosine. We're going to build on these graphs. So typically when we see a function, it's not just going to be one of these, what we think of as parent functions. You talked about parent functions in previous math classes. We have a quadratic parent function, a square root parent function, lots of different parent functions, and they give us the basic shape for a particular type of graph. Well, what happens is we add on different numbers. We need to answer that kind of question. What's going to happen to these particular graphs as we add additional constants into our function? So we'll talk about that in a minute. Before we do that, though, I want you to get your graphing calculator out. I want to talk about how we would put these functions into the graphing calculator. Now, anytime we evaluate a trig function using the graphing calculator, the place we need to start is with our mode. So we have to keep in mind, because we're inputting angles, angles can be represented in a variety of ways. So we have to make sure that our calculator knows what type of angle measure we're looking at here. Here we're thinking of inputting radian measures and then again outputting values on the unit circle, coordinates on the unit circle. So even though we're not specifically evaluating the function in the sense that we're typing in sine, plugging in a value, and pressing enter, because our calculator is evaluating these functions in order to get ordered pairs to plot, we do still have to adhere to this requirement to be in the correct mode. So before you actually type in your function, you're going to want to double check that you're in the right mode. So if you look at the mode, double check that you're in radian mode. Our inputs are being represented as radians, so we need to make sure that our calculator is in radian mode and is going to interpret all of those inputs correctly. Okay, so once we're good there, you can get out of there, go into y equals, and then you're going to type in your function. So let's do the sine function first. So I'm just going to graph sine of x, and then I'm going to hit graph, and let's see what we get. Okay. So that looks roughly like the graph we expect to get. Notice the wave. So notice we have a point at the origin, which is what we expect, and then we have this wave behavior as we continue around, and the shape is going to repeat forever and ever in either direction. So this is based on a standard zoom and the fact that everything has been squared off and the scale is the same in any direction. There's also a specific zoom setting that's going to be ideal whenever we graph trigonometric functions. So if you go into the zoom menu, you're looking for zoom trig, which on my calculator is going to be option 7. So I'm going to scroll down, and we're going to do option 7, zoom trig, and then I'm going to press enter. And it's going to graph the same graph, but it's going to zoom in a little bit. And the way we have everything distributed is so that the tick marks correspond to multiples of pi over 2. So once we reach this first tick mark along the x-axis, where our sine function maximizes, where it has its highest value, that x value is going to be pi over 2 radians. And then we go to pi, and then 3 pi over 2, and then 2 pi radians, and then we've completed one cycle, and then the graph is going to repeat. So this particular zoom setting is going to be ideal for viewing your trig graphs in the easiest way. Now, of course, you can zoom and move around if you want. You can change your window settings to look at different portions of the graph. But if you're just graphing a standard sine or cosine function, this is going to be a good zoom setting to use. Now let's put the cosine graph in there, and I'm going to leave the sine function on here and then add in the cosine function. And notice on my calculator, it's going to graph in 2 different colors. So the sine graph will already be there, and then it's going to add the cosine graph. And the cosine graph is given in red. So again, notice the cosine starts at its maximum. So when x is 0, when our radian measure is 0, the cosine is at its maximum. And then at pi over 2, we decrease to 0. At pi, we decrease down to the minimum at -1. And then we continue around and then complete a full period once we reach 2 pi. What I want you to notice here looking at these graphs though is notice how similar the shapes are. They are actually the same shape. If you were to take the cosine graph or the sine graph, one or the other, and shift it by pi over 2 units in a particular direction, then you would have a graph that lays on top of the other one. The sine and cosine graphs are very closely related in the sense that you could take one and if you were to shift it, it would essentially be the same as the graph of the other function. We're going to find these kinds of similarities as we graph more complicated versions of these functions. But just again, notice that the shapes are going to be the same. The only thing they differ by is a little bit of distance, horizontally speaking. Okay, so now let's talk about the general functions. What happens when we have other constants within our sine or cosine function? How do we interpret each of those? So our general sine or cosine function is going to be of the following form. So I'm going to put in every possible constant we could have, essentially. And so keep in mind, sine could also be cosine, same thing. So a times the sine of bx minus c plus d. That's going to be our general form for our function. And just to be sure, let's put a y equals there. Could be y equals, could be f of x, whatever we want. Now here, every single one of these constants, notice we've added in 4 constants. Here's x, here's our input. A, B, C, and D, we have 4 additional constants. Each constant in this form represents a possible transformation to that original parent graph of sine or cosine. So we have 4 different possible constants that could appear in our particular function, and each one is going to change the standard graph in a specific way. So the constant a is multiplied out in front of our trigonometric function, either sine or cosine. Now, if we're talking about just a standard graph, not necessarily something trigonometric, just one of our standard parent functions, anytime we multiply by a constant in front of the function, that's going to be a vertical stretch or compression. So in other words, we're going to stretch it vertically away from the x-axis, or going to compress it vertically towards the x-axis, depending upon the value for a. We're going to see the same kind of behavior when we look at a trigonometric function, but we have a different name other than vertical stretch or shrink to represent what's happening to this graph. This constant a represents what we call the amplitude of our graph. So when we're talking about a graph that looks like a wave has an amplitude. So the amplitude of our sine or cosine function is defined as the absolute value of whatever a is. So if a is already a positive number, the absolute value doesn't do anything. If a were a negative number, it's going to take that and it's going to make it positive. So amplitude is always defined as being a positive number. Amplitude represents the wave height, or more specifically, the distance between the graph and its center line. Now for the standard sine and cosine graph, the center line is originally at y equals 0, but it can potentially move. So when we think about amplitude, just to give you a sense, look at the picture. When we think about amplitude for one of these graphs, the amplitude is how high, and of course also how low, the graph is going to reach from that central line. So here on the sine graph, we can go up 1 unit, that's going to be the height of the wave, and we can also go down 1 unit, that's going to be the height of the wave below. So this height of 1 unit in either direction represents the amplitude of this particular wave. And we see the same thing with the cosine graph as well. We just see it in different locations on the function's graph. So the highest value we reach is 1, the lowest value we reach is -1, so the wave height is going to be 1. Now again, the amplitude is always defined as being a positive number, but what if a itself were a negative number and we took the absolute value specifically to get the amplitude? If a is negative, then the function is also reflected vertically. So we essentially have 2 transformations to the original function. So the negative is not considered part of the amplitude, but it does have an impact on the graph. It's going to take everything above the x-axis and flip it below, everything below and flip it above the x-axis. Now what if we have a constant multiplied by our input, by x? When we look at standard parent functions, this is going to give us a horizontal stretch or shrink. So it's either going to stretch the graph outward or it's going to compress it inward towards the y-axis. So the actual period, this is going to change the period of the function. It's going to change how far it takes for the function values to start to repeat. So whenever b is something that's bigger than 1, it's actually going to shrink the period. Whenever b is something that is less than 1, it's going to stretch the period. It's going to make it longer. Now the periods for our original two functions are 2 pi units. That's the horizontal distance after which our function starts to repeat its outputs. So sine has a period of 2 pi, and then cosine also has a period of 2 pi, and then it starts to repeat. If we have a constant in place of b, that's going to change the period, and the new period is going to be the old period, which is 2 pi, divided by whatever that constant b is. And again, the period is defined as the horizontal distance after which all y values or outputs are going to repeat. So if b is something bigger than 1, we're taking 2 pi, dividing, it makes it smaller. That means we repeat our y values across a shorter distance. If b is something less than 1, then division is going to make the period larger. It's going to stretch it out, and it means it takes a longer period of time for our y values to start to repeat. And this right here, this is going to be really important from a practical standpoint once we start to graph. We need to think about where the full cycle of the graph is. In other words, if we want to graph that single period, well, where does the period start and where does it end? What's the interval going to be over which we graph? So one full cycle of each graph, specifically one full cycle, one period, we can think of it as a single period of each of our graphs, is given on this interval. So the standard interval goes from 0 to 2 pi. Our input, representing our radian measure, also has to go from 0 to 2 pi. So the standard interval we graph on, from 0 to 2 pi, our actual input is also going to be graphed from 0 to 2 pi. Why is this inequality important? Well, if we have values inside our trig function changing, altering our x value, that changes how we're going to repeat. It changes what that's going to look like, what the graph is going to look like horizontally. So if our standard graph repeats over the interval from 0 to 2 pi, that's how far we graph, and then we repeat in either direction, knowing how these bounds are affected by the specific constants we have inside of our function is going to tell us what the new interval is over which we graph. So we'll look a little bit more at that once we actually have some numbers, but just keep that in the back of your mind. Normally we go from 0 to 2 pi. We can potentially change that if we're changing the input from something other than just x. Now the constant c, something added or subtracted onto our input, that typically represents a horizontal shift if we're talking about standard parent functions. When we're talking about trig functions, we refer to a horizontal shift as a phase shift. So we're shifting phase. The phase shift, the amount of the shift, is going to be defined as c divided by b. In other words, technically speaking, we would want to factor out b before we do anything. We would divide it out from c. And so whatever that constant is, that represents how far we're shifting our graph. Are we shifting it left? Are we shifting it right? So a phase shift is a shift horizontally. Now, if the argument is of the form bx plus c, the argument is going to be the input for our function. If it is of the function, or of the form, bx plus c, we're adding on, the value we're adding on is positive, then the graph is shifted to the left. And if it's of the form bx minus c, then the graph is shifted to the right. This was one of those weird special cases you looked at when you looked at standard graphing of transformations. X does the opposite. I always teach my students X lies. It does the opposite of what you'd expect. So if you're subtracting from the x value, you'd expect it to go negative. It does the opposite. It actually goes towards the right. And if we're adding, we'd expect it to be positive, to become more positive. It actually shifts and goes to the left, and it's more negative. So you do the opposite of what the sign tells you to do when you're looking at a phase shift and a horizontal shift. And then the last constant we can have is one added on to the function as a whole, and that represents a vertical shift. So our vertical shift, the amount of it is just going to be our value for d. So if d is positive, we're adding on a number, then the graph is shifted up. And if d is negative, then the graph is shifted down, just like with our standard parent functions other than our trig functions. Now, one thing we do need to keep in mind, if there is both a vertical shift and an amplitude change, we're changing the height of the wave from something to other than 1, then we have to be mindful of both at the same time. You have to apply both transformations. My recommendation is do the vertical shift first and then do the amplitude change. When we think of the function as shifting vertically, we have to keep in mind that everything shifts. And more specifically, what's going to shift when we think about the function shifting? Of course, the graph itself is going to shift, but fundamentally speaking, the location of this central line is going to shift, the line that divides this function into equal parts above and below. So that standard central line is on the x-axis there at y equals 0. If we're adding on or subtracting from our function, it's either going to shift that line upward or it's going to shift it downward. So if you can shift that vertical line, then essentially all you have to do is translate the locations of these points onto that new line. But if we're shifting and we're stretching the graph at the same time, it's going to be easier to do the shift first and then stretch from the new location of that line. So again, we'll look at that in detail with some actual numbers, and that'll make more sense once we get to that point. So that's going to represent all of our different situations. Now we're just going to look at examples, how we go about graphing each of these. Now the most important thing you're going to do is labeling. Once you've labeled everything, essentially all you're doing is translating those key points onto your graph based on which of the two trig functions you're looking at. Is it sine? Is it cosine? So as long as you know the shape of the graph, that's half of the problem right there. The rest of it is based on how you label things. What does the graph look like vertically? What does the graph look like horizontally? So on and so forth. So we want to graph one period of this transformed function, y is equal to 4 times the sine of 3x, and then we want to identify the amplitude and the period of this function. So we're going to actually start by identifying the amplitude and the period. So notice in this case, we have a value for A, and we have a value for B, and we don't have anything for C or D, so the corresponding transformations there are not going to apply in this case. So A is going to give us the value for our amplitude. So the amplitude in this case is going to be the absolute value of 4, which is 4. So this is going to be the wave height. This is going to tell us how far our graph stretches from its central line. Now because we aren't shifting anywhere, we know our central line is staying here at 0. So I'm going to label this as 0. And then our graph is going to stretch 4 units vertically in either direction. Now you might want to mark it as 1, 2, 3, 4. You don't have to do that. All you have to do is label where your max is and where your min is. It's all about labeling. So in this case, because our amplitude is 4, our maximum is at positive 4 and our minimum is at negative 4. So that takes care of the y-axis. Now why did I label 0 over here? I labeled 0 over here so that we can potentially put a different label here. So we're going to label all of the key x values starting from this point of intersection. And so if we want to label something vertically, I'm going to label the vertical value out here next to the x-axis. So our key y values are going to be at 4, 0, and negative 4. Okay, now our period. What's the period going to be? Well, the standard period for sine is going to be 2 pi. And this value for b changes that period based on division. So if we take our standard period and divide by whatever number we have, represented by b, that is going to be our new period. So what this essentially means is, whereas the standard sine graph repeats after 2 pi units, this particular graph is going to repeat in a third of the time. It's going to repeat after 2 pi over 3 units. So essentially imagine taking that standard sine graph and then shrinking it down so that it repeats over less different distance. Now what we want to know is, what's the actual cycle going to look like? How are we going to cycle as we go across the whole period of this function? So our standard cycle for our standard input goes from 0 to 2 pi. What we want to determine is, how does this change on our input affect that cycle? So our standard cycle goes from 0 to 2 pi, which means our input, 3x, is also graphed from 0 to 2 pi. Well, what we want to know is, based on our actual input, what's going to be the effect on our variable x, since we're graphing with respect to x. So this is x, this is y. We're graphing with respect to x. So what is the impact on the actual value x, what we're graphing with respect to? So we're going to divide out that coefficient from all three parts, which is going to give us 0 is less than or equal to x is less than or equal to 2 pi over 3. So what that tells me is that if I graph a single period, in other words, the period from 0 to 2 pi, but the version of it that it's been transformed, I'm going to graph from x equals 0 to x equals 2 pi over 3. So my x values are going to start at 0, and they're going to end at 2 pi over 3. Now, before I put that on there, I want to go back and look at the standard sine graph. What I want you to notice is that there are 5 key points that we use to get the shape of the sine graph. Every time we graph a sine function, we're looking for the new versions of these 5 key points. How do the new constants in the function affect the location of those 5 key points? But what we're ultimately focused on is, what would the labeling be based on how our function has been transformed. So we have the location where we start, and then from there we have 1, 2, 3, 4 tick marks that are going to label the additional key locations. So what I want to know is, where are those tick marks? I'm going to go ahead and put those 4 tick marks on here. 1, 2, 3, 4. And based on what we just determined, our full cycle is going to go, rather from 0 to 2 pi, it's going to go from 0 to 2 pi over 3. So our period is going to start at 0, and it's going to go to 2 pi over 3. So what happens in the middle? Well, one thing I want you to keep in mind is, because this graph was generated from the unit circle, when we graphed these particular key points, they were graphed over equal intervals. They were graphed as we traveled from one axis to another and passed through each of the 4 quadrants. So what that means is that we have 1, 2, 3, 4 equally sized intervals on our graph, each one of them representing a quadrant. So here's the first quadrant, here's the second quadrant, here's the third, and here's the fourth to take us back full circle. So how far apart do these marks have to be? How large do things have to be in order to take us, rather from 0 to 2 pi, to take us from 0 to 2 pi over 3? So how far apart do each of these have to be? That's what I'm going to refer to as graphing increments. How are we increasing incrementally along the x-axis to get from where our cycle starts to where it ends? Well, again, we have to think of it as how many intervals we have. They're equally sized. Well, we have 1, 2, 3, 4 intervals, all of equal size. So the actual distance from where we start to where we finish is 2 pi over 3. So if we take 2 pi over 3 and divide it up into 4 equal parts, that will tell us how far apart each one of these marks is, and that's going to help us label everything we need from there. So our actual increments are going to be 2 pi over 3, the period divided by 4 units apart. In other words, we're taking our period, dividing the full period into 4 equal parts in order to label where those new increments are going to be. So let's figure out what that's going to be. So that's going to be 2 pi over 3 times 1/4. I have that common factor of 2. I can divide that out. So that's going to be pi over 6. So as we travel from the beginning of our cycle to the end of our cycle, we're moving by pi over 6 units at a time. So each increment is pi over 6 units from the previous one. So let's see if we can label just knowing that. We start at 0 and we're counting by pi over 6 in order to get from the start of our cycle to the end of our cycle. So 0, and then we move by pi over 6, so that's going to take us to pi over 6. Okay, so 0 to pi over 6. Now we add on an additional pi over 6, which will take us to 2 pi over 6, otherwise known as pi over 3. And then add on an additional 1, it'll take us to 3 pi over 6, otherwise known as pi over 2. And then if we've done everything right, if we've counted right, let's see what happens now. We already had this labeled, so we go from 3 pi over 6 to 4 pi over 6, which reduces to 2 pi over 3. So that's a verification that these are going to make sense. Now, if you need to do this algebraically, that's perfectly fine. The general idea is that we're starting at 0 and we're counting by pi over 6. So from 0, we're adding on pi over 6 units in order to get to our next tick mark. And that's going to take us to pi over 6. Now, from pi over 6, we're adding on an additional increment. So we're adding on an additional pi over 6, which is going to give us 2 pi over 6, which reduces to pi over 3. From pi over 3, we're adding an additional pi over 6. Okay, we know pi over 3 is the same thing as 2 pi over 6. So we're taking 2 pi over 6 and adding on pi over 6, which is going to give us 3 pi over 6, which reduces to pi over 2. And then from pi over 2, we're adding on an additional pi over 6. So this will be the first tick mark, second, third, and then add on an additional 1, it'll take you to the last one. So rather than writing it as pi over 2, let's write it as the one that already has the matching denominator. Let's write it as that version. So 3 pi over 6, and we're adding on one additional increment, which is going to take us to 4 pi over 6. In other words, 2 pi over 3, where our cycle is supposed to end. So if you need to work it out algebraically, which sometimes will be beneficial, this is how you can do that. So that means these 4 values are going to be the labels for our tick marks, as we've already seen. So once I have everything labeled, everything has been taken care of. All I have to do is put in the key points based on the fact that we're graphing a sine function. So let's go back and look at the standard sine. What's the general idea for how the sine is changing across that one period? Well, it's starting on the center line at its starting point, and then we increase to the maximum, go back to the center line, decrease to the minimum, and then go back to the center line. This shape is the standard shape for a sine graph, and it's what we're going to see with these particular x and y values. So we start at the center line, and then sine increases to its maximum. We go back to our center line, we decrease to our minimum, and then to complete the period, we go back to the center line. And so I can connect my dots, and that's going to give me the graph of my sine function. Now let's see if this makes sense based on what we can see on the graphing calculator. So the graphing calculator is going to be relatively limited in terms of what it can show you about actual values, but we can at least compare what we're seeing here with what we'd see on the original sine graph. So let's go back to y equals, and let's clear out the cosine graph. But we want to add the actual function that we graphed and maybe compare it to the original sine graph. So we're graphing 4 times the sine of 3x. And so we decided that that 4 stretched the graph vertically, it gave it a taller wave, and the 3 shrunk the period so that rather than repeating over 2 pi units, we're repeating over 2 pi over 3 units. So there we go. So we can see the height of the wave, it's stretched. The original wave maximizes at 1. This wave maximizes at 4. And then we repeat over less time. So what you're looking for is the general shape you follow until the shape starts to repeat. So starting there from 0, 0, we repeat once we get to this point. So our standard graph repeats over 2 pi units. This graph repeats over 2 pi over 3 units. So a third of the distance. Now we can't really see this particular shape from our actual graph, but because the labeling is there, we do have the same graph, just graphed in a little bit of a simpler manner. Okay, let's look at another one. Okay, again, we want to graph one period of this function, identify its amplitude, identify its period. Notice again, we don't have a phase shift, we don't have a vertical shift. We have a value for A, we have a value for B. So we're changing the amplitude from 1, and then we're changing the period based on this value of B. So the amplitude is defined as the absolute value of that coefficient out front. Now the coefficient is negative, so we do have to take the absolute value. So the amplitude in this case is going to be 1/2. But what does that negative mean? That negative means we also have a vertical reflection. So we can't forget that. As we graph, we're going to have to make sure we take care of that vertical reflection. So the height of the wave has shrunk. It goes from a height of 1 to a height of 1/2. And then we're also reflecting the points over the x-axis. So let's label our y values based on that. We're not shifting up or down, we're just changing the height of the wave. So our center line stays where it is, we haven't shifted anything. But now we maximize at 1/2 and we minimize at negative 1/2. Okay, now what about the period of the function? Well, our standard period is 2 pi, and we're dividing it by whatever our value is for B. In this case, our value for B is pi. So in this case, that common factor reduces, and we're left with 2. So rather than repeating over 2 pi units, the graph of this function is going to repeat over 2 units. Notice the pi completely disappeared. That also means as we count our increments to graph, the increments aren't going to involve pi. If the period doesn't involve pi, the increments aren't going to involve pi either. So what's the full cycle going to look like? The standard cycle goes from 0 to 2 pi. Well, how does the addition of this constant affect that cycle? So our standard cycle goes from 0 to 2 pi, but that has been changed by this coefficient. So we want to know, based on the addition of this coefficient, what's the impact on x, what we're actually graphing over. So we want to divide out pi to solve for x and determine the appropriate interval for x. So divide by pi, make sure you divide all 3 parts. So this common factor reduces, and notice it also reduces over here. 0 divided by anything is just going to be 0. So 0 is less than or equal to x, is less than or equal to 2. So that tells us where our cycle is going to start and where our cycle is going to end. Now, how do we label everything in the middle? Let's go back and look at the standard cosine graph. Just like sine, we change in a specific way. We graphed a specific number of points. We graphed 1, 2, 3, 4, 5 points. So starting from 0 radians, and then to the first quadrant, second, third, and then back around through the fourth quadrant. So we have a total of 4 additional key locations to take us from where we started to where we have to finish our cycle. So just like with sine, we have those specific intervals over which we graph, or specific increments. So 1, 2, 3, 4, and our cycle starts at 0 and it ends at 2. So the distance from where we start to where we end is going to be 2 units. And then we increase by equally sized increments in between. Think of this as the first quadrant, the second, the third, and the fourth. But what's the impact based on the fact that we now have this new value and we've changed our period? Well, our new period is going to be 2 units, and we're dividing this full period into 4 equally sized parts, which means our increments are 1/2 a unit apart from one another. So in other words, we're counting along our x-axis going by 1/2 a unit at a time. Now this one you can probably do just by counting without really not really needing to write too much out. So we start at 0, and then we're counting by 1/2 to go from increment to increment. So add on 1/2 and we get to 1/2. Add on another 1/2, so 1/2 plus another 1/2 is going to give us 1. Add on another 1/2. We don't call it 1 1/2, we're going to call it 3 halves. So you can think of it as 1/2, 2 halves, which reduces to 1, 3 halves, and then add on an additional 1, and we get to 4 halves, which reduces to 2. So there we go. Once the x-axis is labeled, the y-axis is labeled. All we're doing is putting in the specific points that correspond to our cosine. Now, don't forget the vertical reflection. We can't see the fact that there's a vertical reflection just from the labeling. We have to remember to indicate that vertical reflection when we put in our points. So we're graphing a cosine. Now the cosine is going to start at its maximum and then go back to its central line and then go to the minimum, central line, and then back to the maximum over a single period, and then of course it repeats. Now we're reflecting this vertically, which means the original starts at the maximum. Our graph is going to start at its minimum and then increase and then decrease. So imagine taking this graph, which looks kind of like a U, and then just flipping it upside down, and that's going to be our vertical reflection. Again, based on the fact that we've already labeled, and so that gives us coordinates for our key points. So original cosine starts at its maximum. Our reflected cosine is going to start at its minimum, and then it's going to increase up to its maximum and then decrease again and come full circle back to the minimum value, and then we just fill in the shape from there. And you'll notice I'm kind of skipping spots right here. I just want to avoid writing anything on my actual units. If you want to connect, you can. I would just try to avoid writing on your actual numbers there. So that is going to be our single period. Okay, so we've changed the amplitude, we've changed the period. Let's look at one additional transformation. Okay, so we want to graph one period of this function, y is equal to the cosine of the quantity 2x plus pi over 2, and then identify the amplitude, the period, and in this case we want to identify the phase shift as well. Now it says we want to identify the amplitude, but there doesn't seem to be a new constant representing the amplitude. All that means is that we haven't changed the amplitude. It's going to have the standard amplitude corresponding to the particular function we're graphing. So we're graphing a cosine. We don't have a value for a, so it's understood that our a is going to be 1. All that means is that the amplitude is 1. The wave height is going to be 1. So we maximize at 1, we minimize at -1. Now again, we don't have a vertical shift, which means our central line stays here at 0, and then we have 1 unit up and 1 unit down from there. So our central line is at 0, our maximum is at 1, our minimum is at -1. Okay, now what's our period going to be? So here's B, and here's C. B affects our period. So the standard period for cosine is going to be 2 pi. And we're dividing by whatever B is. In this case, B is going to be 2. So we're dividing by 2, which is going to give us a period of pi. So rather than repeating over 2 pi units, we repeat over half the time. We repeat over pi units. So again, it's like shrinking the graph down horizontally. Now the phase shift is new. We haven't done a phase shift before. So our phase shift, notice we have a number that's positive, which means we're actually going to shift in the negative direction. So the phase shift itself is actually a negative number. It's going to be our value for C, which in this case is negative 1/2, divided by our value for B, which is going to be 2. So we can rewrite that as negative pi over 2 times 1/2, which is going to be negative pi over 4. And specifically, we know it's negative, but you might want to make a note. This is actually going to be to the left. So we're shifting our graph to the left. Now here's where it gets a little bit more complicated to label, and this is why the labeling is so important. 2 horizontal things have changed at this particular point. We've changed the distance over which we repeat. We repeat over pi units rather than repeating over 2 pi units. But we have also shifted everything pi over 4 units to the left. So a couple of things have changed here, not just one thing, but a couple of things have changed. This is where knowing what the cycle looks like is going to be that much more important. What we want to know is what have these constants done to our standard cycle from 0 to 2 pi. In other words, if the standard input goes from 0 to 2 pi, well, what does this specific x go to, given that we have these 2 additional constants involved? So our cycle, standard cycle, is going to go from 0 to 2 pi. And so based on that, since we're graphing with respect to x, where is x going to go? Where's it going to start? Where's it going to finish? So I want to solve for x in this inequality. I'm going to start by subtracting pi over 2 from all 3 sides. Now 2 pi minus pi over 2. 2 pi we can also think of as 4 pi over 2. And so if we're subtracting pi over 2 from that, that's going to take us to 3 pi over 2. And then we're also dividing out a 2 from both of these. And so negative pi over 2 divided by 2 is going to give us negative pi over 4. And then 3 pi over 2 divided by 2 is going to give us 3 pi over 4. So in this case, notice our cycle is not going to start at 0. With the previous 2 examples we did, the cycle still started at 0. It just didn't reach all the way to 2 pi. Here, our cycle is going to go from negative pi over 4 to 3 pi over 4. Now here's where I'm going to kind of leave it up to you how you really want to graph things. I'm going to encourage you to graph this particular way, but I want to explain a little bit more carefully what's really going on here. If we think of this as truly being the origin, then where is our graph actually starting? Well, it's starting at negative pi over 4, which would be somewhere over here to the left. Rather than actually marking negative pi over 4 over here to the left and abandoning this axis I already have, here's what I'm going to do instead. I'm actually just going to mark this intersection as my starting point at negative pi over 4. And then as I graph, because this is no longer the actual y-axis, as I graph, I just need to keep in mind where is the actual y-axis. This is going to be an axis that we use just for sake of ease of graphing. But this is no longer the y-axis because this is no longer x equals 0. It's now x equals negative pi over 4. And so once we get to that point, I'll go back in and I'll show you where the y-axis is. But I find that this is just the easiest way to graph from the standpoint of not having to physically move things and determine how the other components interact in the same way. So I'm just going to label my true starting point at the intersection of these two lines and then worry about where the actual axis is later. Now we know the cosine is graphed over those 4 quadrants, so we have 4 equal increments. So from our starting point, 1, 2, 3, 4, and we know the cycle goes from negative pi over 4 to 3 pi over 4. So this is going to end at 3 pi over 4. And then how far do we go between each increment to go from one to the next? Well, our period is pi, so the distance between where we start and where we end is going to be pi units. Notice because this is not pi and this is not 0, we don't actually have this number and this number matching. But if you were to look at the distance between these two, how far apart these values are, they're pi units apart, which means we have a period of pi. So as we graph, we're taking the whole length of that cycle and dividing it into 4 parts. So each increment is going to be pi over 4 units from the previous one. Now, because our starting point and our end point are already in terms of pi over 4, we can probably just count here and we may not need to actually write out the algebra. So if we're starting at negative pi over 4, and we're traveling by pi over 4 units. We start at negative pi over 4, and then add on a pi over 4, and it takes us to 0. Add on another pi over 4, it takes us to pi over 4. Add on another pi over 4, it's going to take us to 2 pi over 4, otherwise known as pi over 2. And then 2 pi over 4 goes to 3 pi over 4, and we end where we're supposed to. Now, what I want you to notice here, notice this is now where 0 is, which means this is the actual y-axis. This is the actual y-axis. So I'm going to label that just so we know where things really are and we can actually see the shift. So if this is the new y-axis, then truly our starting point is to the left of that, which we expect based on what our phase shift was. Now we just have to put in the points for our cosine based on where we start and where we end. So we know that the general cosine graph is going to start at its maximum, and then it's going to decrease down to its minimum, increase back up. So we start at the maximum, we decrease to the central line, decrease to our minimum, and then back to the central line, and then back up to the minimum. Connect your dots, and we've got our cosine graph. So this one was a little bit different. Graphing with the phase shift is typically what makes the problem more complicated, particularly if there is both a period change and a phase shift. 2 different things are changing horizontally. So not only are we changing how far apart all of our units are, we're also changing where our graph starts and then where it ends. So having a sense of how to work through the cycle, determining what the actual cycle over which we graph is going to be important, and knowing how far apart each incremental unit is going to be important as well. Okay, let's look at another one. Now we haven't seen a vertical shift yet, so let's look at one with a vertical shift. Okay, so we want to graph one period of this function. Y is equal to all of this, 2 times the sine of the quantity, 4x minus 3 pi, plus 5. So we have an A, we have a B, we have a C, and we have a D here. All 4 different transformations are represented. Okay, so let's start with A. A is our amplitude, so we have a 2 there, so the amplitude is going to be the absolute value of 2, which is 2. So that's going to give us the height of the wave from our central line, 2 units up and 2 units down. Now here we have a vertical shift. We've shifted this whole graph up 5 units because we've taken our previous output and we've added on 5 to it. So our vertical shift is going to be positive 5, which means we're shifting up 5 units. Now these two components have to be reconciled at the same time. We have to shift vertically, and then from that location we'll stretch. So I recommend doing the shift first. Most importantly, think about where your standard central line is, and then shift that based on this particular number that's giving us our vertical shift. So the original central line is at 0. It's at y equals 0. Now we're shifting everything up 5 units, which means our original line at 0 is now shifted up, and we're now at y is equal to 5. That's going to be our new central line. Now from that central line, our amplitude is going to be 2 units, which means we have 2 units above to maximize and 2 units below to minimize. So what we have to figure out is from 5, what would the maximum and minimum values be given that we stretch a distance of 2 units in either direction? Well, if we go 2 units upward from 5, that's going to take us to 7. And if we go 2 units downward from 5, that's going to take us to 3. So notice 3 and 7 are 4 units apart because we go 2 units in either direction, but they're centered around this number 5 because we've shifted everything up by 5 units. Now, just like with the previous example where I moved things around and used my lines strategically, this no longer represents the x-axis. This now represents the line y equals 5, which means the actual x-axis is somewhere down here. Now the scale's not great based on me just putting it right there, but you get the idea. That is the actual x-axis down here. So the line we're graphing on, just graphing on for ease, is not the x-axis anymore. The x-axis is somewhere down here, so do keep that in mind. Now our period and our phase shift. Once we have all this labeled, we're good with that. Period and phase shift, we need to go back to that. So our value for b is going to be 4. That's going to affect our period. So the standard period for sine is going to be 2 pi, and we're dividing it by b, dividing it by 4, which is going to give us a new period of pi over 2. So that means from start to finish across the whole cycle, we go pi over 2 units. Now, what about our phase shift? That's from C and B. So C is a negative number. In this case, that means we're shifting to the right. If we're subtracting, we actually think of C as being positive. So our phase shift is going to be positive 3 pi divided by our value for B. And that doesn't reduce, so we can leave that alone. And that's technically going to be to the right. So what is our new graphing cycle going to look like, considering that not only have we shrunk our horizontal distance, but we've also shifted things over to the right? Where is our graph going to start? Where is it going to end? So again, our standard cycle for our standard input is from 0 to 2 pi. But what's the effect on x, given that we have these two new constants here? So 4x minus 3 pi, our input, goes from 0 to 2 pi. So based on that, what are the boundaries on x? So I'm going to solve for x, add 3 pi to all 3 sides. So that's going to be 3 pi is less than or equal to 4x. And then 2 pi plus 3 pi is going to be 5 pi. Okay, and then divide all 3 parts by 4. So that's going to give us 3 pi over 4, and then x, and then 5 pi over 4. So this is where our graph is going to start, and this is where our graph is going to end. Now notice in this case where we're starting is actually going to be towards the right of the y-axis. So if we're going to use our lines, again, strategically to simplify our graphing, we're not starting at 0, we're starting at 3 pi over 4, which means our actual y-axis is somewhere over here. That's our actual y-axis. So essentially, if we were to think about the actual shift we're seeing, we're shifted somewhere into the first quadrant on the XY coordinate plane. Not only have we shifted our period to the right into the positive X values, but we've also shifted the graph up, so we're into the positive Y values. So if we think of this as X and Y, then these are going to be our lines for graphing, and that's how they relate to the X and Y axis. Okay, so we go from 3 pi over 4 to 5 pi over 4. Again, counting by 1, 2, 3, 4 equal increments. 3 pi over 4 to 5 pi over 4. Okay, now our period is pi over 2. These numbers are 2 pi over 4 units apart. In other words, pi over 2 units apart. So that's how our period is reflected here. So how far do we move each time we go from one tick mark to the next? Well, we take our period, which is pi over 2, and we're dividing it into 4 equal parts, which is going to be equivalent to pi over 8. So we're counting by pi over 8 units each time. So maybe you can do it in your head, maybe you can't. If you can't, let's actually write down the algebra to move from one unit to the next so we can label these correctly. So we're starting at 3 pi over 4, and then we're going to add on pi over 8 units. So we need our common denominator. So 3 pi over 4 is going to become 6 pi over 8, and we're adding on pi over 8, which is going to take us to 7 pi over 8. So that will be our next key location, 7 pi over 8. Okay. Now from there we add on an additional pi over 8. So 7 pi over 8 plus pi over 8 is going to take us to 8 pi over 8 plus pi over 8. Or excuse me, not that. 8 pi over 8, which just reduces to pi. There we go. Okay, so halfway between 3 pi over 4 and 5 pi over 4 is going to be pi. And then we need to add on one more. So let's see if we can see the pattern. So we have 6 pi over 8. 3 pi over 4 is otherwise known as 6 pi over 8. So 6 pi over 8, 7 pi over 8, 8 pi over 8, which reduces to pi, and then 9 pi over 8, which doesn't reduce, and then 10 pi over 8, which reduces to 5 pi over 4. There we go. So we have all our tick marks represented. Now we can just put in our actual values, knowing that we're graphing sine. So sine starts from its central line. It's not going to start at 0. Here's where 0, 0 is at this point. We're starting up here at this particular location along this new central line. So we start on the central line, and then we go up to the maximum, back to the central line, down to the minimum, and then back to the central line. There we go. That's going to be our graph. Now let's see what this one looks like if we graph it. So let's go back in here. We still have our sine, so let's clear that out. Let's see what this one's going to look like. So 2 times the sine of 4x minus 3 pi. Make sure you close your parentheses after the 3 pi. And then to that we're adding on 5. So let's see what that looks like. So remember, with this graph, this is not truly the origin. This is a point somewhere in the first quadrant. The actual origin is down here. So when we graph this with respect to the original graph, it should be shifted upwards and towards the right. So let's see what this looks like. There we go. So notice it kind of falls off the graph. So if we wanted, we can move things around with the window setting. But we have a shorter period. We can see the shorter period. It's shrunk down. We went from a period of 2 pi to a quarter of the distance to pi over 2. So this graph is actually going to repeat over just pi over 2 units. It's going to repeat in a fourth of the time. and then we're shifted upward and we're shifted towards the right. Now seeing the phase shift is a little bit more difficult, but what you could do is you could of course verify that the ordered pairs match up with what you expect. Now what are we going to see if we look at a table here? Because in a lot of cases when we do transformations we look at the table to get the actual points. The table is only going to be so helpful because it's giving you x values in terms of single units, not in terms of pi over 2 or anything in relation to pi. So these y values may not be as informative as you would like. So just keep that in mind. You can change the table settings to get actual x values that you like, but sometimes it's going to be a little bit more complicated than you would otherwise like it to be. Now that being said, let me show you a way that you can check at least these key points. Let's actually check these. I'm going to go into the table settings. So go into the table settings. Don't worry about table start, anything like that. But what we want is to change our independent variable, which is going to be our input, to ask. As long as you leave everything on auto, it's going to automatically generate your x and y values for you based on where you're starting in your table and how you're moving. So what this tells us is that we're starting at a table value of x equals -1, and we're counting by 1 unit each time, which is why you saw -1, 0, 1, and then so on and so forth. If we change it to independent, or change independent to ask, let's see what the new table looks like. Well, it looks blank because it wants you to input your own x value. Well, let's input these actual x values. These are our proposed x values corresponding to these key values. And let's see what happens specifically on the second graph, because that was the transformed one. So our first input was 3 pi over 4. So 3 pi divided by 4. And supposedly our y value is at 5. So if we type that in and press enter, well, there we go. That checks out and that gives us 5. Now notice on x it doesn't say 3 pi over 4, it gives us an approximation for it. And so this will be the original value for sine at that particular location. This is going to be the transformed value based on all these additional numbers that we have. Okay, so 3 pi over 4, we're at 5. 7 pi over 8 was our next key x value, and supposedly it's 7 pi over 8. We've made it up to 7. Sure enough, that checks out. The next key x value was just pi itself. We make it back to 5. The next one was 9 pi over 8. We make it down to 3, which is again what we expect. And then we should come full circle at 5 pi over 4, and certainly we do. So that's going to help you check your values. Again, keep in mind that your standard table is not necessarily set up to generate these kinds of values, even if you're looking at the graph using that trig zoom feature. So if you want to change it so that you can access these values, the easiest way to do it is to change your table settings and take your independent variable, set it to ask, so you can type in values, and then type in those key x values and see if your y values match. Now once you do that though, make sure afterwards that you go back and you reverse your table settings. Otherwise you may end up with a table that's confusing. So after you do that, it's a good idea just to otherwise leave things on auto. And so then if you go back into your table, notice it takes you back to where you were. So you can play around with that a little bit as long as you remember the settings that you changed, and make sure to go back and fix those afterward. Okay, let's look at one more special situation. There's one potential transformation or situation that we haven't really dealt with. So we've looked at a vertical stretch, a vertical shrink, horizontal stretch, horizontal shrink. We called that an amplitude change, and then a period change for our periodic functions. We've looked at a shift left and right. We've looked at a vertical shift. The shift left and right, we call that a phase shift. We had a vertical shift as part of the amplitude change. If the number in front of our trig function that we're multiplying by is a negative number, then we know that we have a vertical reflection. The one type of transformation we haven't seen that we know can happen with functions is a horizontal reflection. Well, we would get a horizontal reflection multiplying out front of our variable by a negative. But the problem with trying to reflect a graph like this horizontally is because it repeats indefinitely, you're having to reflect a lot of points. So actually executing a horizontal reflection is relatively complicated from a graphing standpoint. So what we can use alternatively is the fact that sine is an odd function and cosine is an even function. Those even-odd rules allow us to deal with those situations where there's a negative in front of our x value inside of our trig function. They're going to allow us to deal with this in such a way that we can essentially eliminate that negative and then interpret it in a different way. So when we consider a period change and a phase shift, in other words, transformations that are inside of our trig function, we want to make sure to factor out any negative that's out front of the value b. Factor it out. Specifically factor it, it's still going to be inside of our trig function, but you want to factor it out of the two terms inside of the trig function. And then you're going to use the parity properties to simplify this situation with the negative. So you're going to run into one of two cases, one for sine, one for cosine. So for sine, sine is an odd function, which means that sine of a negative value is going to be the negative of the original sine. And then cosine is an even function, which means cosine of a negative is going to be the same thing as cosine of the positive. Essentially, the negative goes away. So if we can rewrite our argument for our function as a negative times a larger argument, factor out that negative, then we can use one of these two rules in order to graph. So we want to graph one period of this function, 3 times the sine of the quantity, negative pi over 4 times x minus pi over 2, all of that minus 4. And again, identify all of these key features. So before we do anything else, we want to rewrite everything with a positive coefficient on x. In other words, this negative out here, this is the problem. We don't want to deal with that. We want to use the even-odd rules to take care of that negative. So I want to take this binomial inside of my sine, and I want to factor out the negative out front. In other words, divide it out from the first term and then also divide it out from that second term, but leave it so that it's still inside of my sine function. So if I factor it out, just factoring it out that far, I'm going to have 3 times the sine of negative what? Negative what's left over. So factor out a negative from the first term, factor it out from the second term, which is going to take both of these and make them positive. So that'll become positive pi over 4 times x plus pi over 2. And then we still have our minus 4 out there. So forget about all this for a minute. We now just have the sine of a negative input, okay? And sine of a negative input, the parity rule, the fact that sine is odd, tells me that I can essentially pull out that negative out front. It becomes the negative sine, and that allows me to eliminate the negative on the inside. So this is going to become negative 3 times the sine of this altered input, pi over 4x plus pi over 2 minus 4. Okay, well, once we're in that form, we have everything we need. So here's our A, here's our B, here's our C, here's our D. Okay, so A in this case is negative 3, so our amplitude is the absolute value of negative 3, which is going to be 3. Because there's a negative, we're going to have a vertical reflection. So I'm going to make a note of that here. Okay, now we also have a value for D. Both of those correspond to vertical transformations. So because we're subtracting 4 from the entire function, our vertical shift is going to be negative 4, which is going to shift us down. So let's go ahead and label our graph based on these two transformations. So everything on our graph is going to shift down by 4 units. And then from our new central line, we have an amplitude of 3, a wave height of 3. So down 4 units. The original central line is at 0. We're going down 4 units. So the new central line is at -4. And then from -4, we have an amplitude of 3. So 3 units above and 3 units below -4. So 3 units above would take us to -1, and 3 units below would take us to -7. So as with a couple of the previous examples, keep in mind this means that we're no longer working with an actual axis. This is no longer the x-axis. If this is -1, this is -4, and this is -7, well, that means the x-axis is somewhere up here. It's going to be above -1. So we're now working with a graph that's below the x-axis. Keep that in mind. Okay, so we've taken care of the vertical component of our graph. What about the horizontal component? So specifically, what's our period going to be? Well, we're looking at sine. Sine has an original period of 2 pi. And then based on our new version of our equation, our value for b is going to be pi over 4. So we're dividing 2 pi by pi over 4, which we can rewrite as 2 pi times 4 over pi, which means that common factor of pi is actually eliminated, and we just have 2 times 4, which is going to give us 8. So our period is going to be 8 units long. So rather than 0 to 2 pi, it's going to be 0 to 8, or potentially 0 to 8 shifted. 8 units across to complete one cycle. Now what about our phase shift? What does that look like? Well, we have a value for C and we have a value for B. So C in this case is positive, or we're adding C, which means the actual value for C from the perspective of the phase shift is going to be negative, and then we're dividing by our value for B. So because we're adding, it's going to shift our graph to the left. And then let's execute this. So negative pi over 2 times 4 over pi, keep change flip, reduce that common factor. Don't forget your negative, that's still there. So negative 4 over 2 is going to be -2. So start to finish, our starting point and our ending point are 8 units apart, and all of our points are shifted 2 units to the left from where they would originally be. So what are our actual marks going to be? What's our actual cycle going to look like? Well, make sure you're using the positive coefficient version of your equation when you do this. So standard cycle goes from 0 to 2 pi, which means our actual input is going to go from 0 to 2 pi. So pi over 4x plus pi over 2 goes from 0 to 2 pi. So what is the impact on x in this case, because we're adding and multiplying? We need to subtract the pi over 2, so negative pi over 2 is less than or equal to pi over 4x. And then 2 pi we could write as 4 pi over 2. And so if we subtract pi over 2, that's going to give us 3 pi over 2. Well, now we're dividing by pi over 4. Alternatively, we can think of it as multiplication by 4 over pi, which is going to allow us to write it out a little bit more easily, show our work a little bit more easily, and see what's happening specifically with these pi's. So notice that common factor reduces down in both of our boundaries. So 4, so negative 4 divided by 2, that's going to be -2. We have our x in the middle. And then on the right-hand side, 3 times 4 is going to be 12, and 12 divided by 2 is going to be 6. So our new endpoints are going to be -2 and 6. And notice again how this is related to the period. How far apart are -2 and 6? Well, they're 8 units apart, hence the period of 8 units. Well, what are our increments going to be here? If we take the period of 8 and divide it into 4 equal parts, how far apart are each of them? Well, they're each going to be 2 units apart. So in other words, we're starting at -2, ending at 6, and counting by increments of 2 to go from one key value to the next. So our graph is going to start at -2, and then 1, 2, 3, 4 equal increments, and it's going to end at 6. So if this is -2, remember our graph is shifted over to the left some. We're starting to the left of the y-axis, and we're counting by 2 units each time. So -2, add on 2 is going to take us to 0. Add on 2 again is going to take us to 2. Add on 2, it's going to take us to 4. And then add on 2, we end at 6. So here's something to notice. The x-axis is above our grid. Here's the y-axis. If that's where x is equal to 0, that is going to be our y-axis right there. Okay, so we've got all of that. We've got all of our labels. We're graphing sine. Here's our central line. Here's our vertical. So we're starting at this particular location right here. Okay, so sine starts from the center. We go up to our maximum. Oops, what did I do wrong? I did something wrong. I'm graphing this particular one. What should I be graphing? I should be graphing this one, the alternate version. Let me box that in. There we go. That's better. I'm boxing this one in because I'm using this one. What did I do wrong? Well, everything looks right except that vertical reflection, right? So this point, that's wrong. It should be reflected, right? So we're starting at the center. We go down to the minimum, and then up to our maximum, and then back down to the central line. There we go. That's better. That is going to be our graph. So do something other than what I did. Make sure you box in this altered version of your equation before you start working so you don't make the mistake that I just did. So this point does not exist. This is going to be our actual graph. Now, as with the previous one, let's go back and let's actually check these values. So I'm going to go back into y equals, clear out the previous one we graphed. So where is our actual graph? Well, again, it's below the x-axis. The period we graphed is below the x-axis, and we're staggered over the y-axis. So the beginning of our graph is to the left of the y-axis, and then we cross over the y-axis as we continue that period. So let's actually type in the original function and see what happens. So we're going to graph the original one. Now, careful as you type this in. You'll want to put parentheses around that -pi/4 before you multiply it by x, just to be safe. And then you may want to put parentheses around the pi/2 once you subtract it, just so your calculator truly understands where your fractions are supposed to go. So parentheses around -pi/4, parentheses around pi/2, and then it's multiplied by x, and then parentheses around all of that, because all of that is your argument for the sine function. And then we're subtracting 4 from there. So let's graph that. Oops, syntax error, go to. Let's see, what did I do? Oh, what did I do? I put in a subtraction sign. There we go. Let's try that again. So now that's a negative. Now we can graph it. There we go. So again, notice we're below the x-axis, which is what we intended. Seeing the shift, seeing the period change is a little bit more difficult here. But how do we again verify that these numbers make sense? Use the table. Now here, because we're actually counting by something other than units related to pi, based on the actual changes we saw, we may not have to actually change anything in our table. So let's see what we can see. Well, our starting point had an x value of -2, and we said the associated y value was -4. Well, there's -2, -4, so that starting point is on there. Because of that vertical reflection, we then minimized, so our next point had an x value of 0, and then a y value of -7. Okay, that's there, that one's correct. Our next one, we went to x equals 2, and we were back to a y value of -4, so that's going to be there as well. Next, x value was 4, and we were up at -1. That was our maximum. and then we had an x value of 6, and we were back to that central line at -4. So believe it or not, this actually works out. It's actually the correct points. It's at the actual correct values at that point. So that gives you a few examples of the different kinds of transformations you could see, both for the sine graph and for the cosine graph. As you can see, graphing these kinds of functions is fairly involved. So going through the steps to actually understand what's happening algebraically for each of these transformations is going to be important. You're going to want to take your time with these. My recommendation is, before you try graphing all of these on your own, you might want to go back and get a clean sheet of paper and just regraph the ones you have here in the notes. Because you now have an accurate graph to base those off of, take a moment and regraph those and make sure you understand what's going on with these particular graphs, and then use these as the models for the other ones you graph.